a recent GIS and remote sensing graduate from the University. I have been serving as a GIS engineering solution intern here at ESRI Eastern Africa for the past 3 months. And I hold a bachelor or degree of science in geographic information system and remote sensing. I am deeply passionate about using geospatial technology to solve real world challenges, especially in urban planning, disaster management, and environmental conservation. Uh, Throughout my internship, I learned how to integrate multiple ArcGIS tools to design smart applications and communicate findings in a clear visual way. So it has been a meaningful step in my career as a GIS professional. So today I'm excited to present my final project titled Modernizing Fire Department Operations with ArcGIS. This project focuses on how spatial technology can transform fire service operations by improving fire risk assessment, response planning, fire safety inspections, and communication hazard mapping. I believe modernizing fire department operation through ArcGIS system is not just about map or technology or just about system, but also protecting lives and properties, also resilient cities. Uh, the fire department, which have been focused on, it is Tanzania Fire and Rescue Force. It is a national agency at the Ministry of Home Affairs. And the main responsibility of this fire department is responsible for fire prevention, rescue, and emergency response across the city. And its mission is to be East African leading fire and rescue service by 2025 with a focus on professionalism and public safety. Recently, the government uh, did some improvements that can help the operations of fire departments by including the acquisitions of 12 modern firefighting vehicles in May 2024, with future plans to add a helicopter and 150 more vehicles to enhance emergency response. But despite these advancements made by government, the fire department faced challenges in limited data for planning, data management, outdated inspection system, proactive risk assessment. So by integrating GIS, particularly the ArcGIS system, presents an opportunity to address these challenges by enhancing spatial planning, situational awareness, and community engagement. The pilot area for this project, it is Dar es Salaam City. As we know, the Dar es Salaam is a complex urban environment combined with its vulnerability to fire hazard and commitment to modernization, make it a perfect case study for demonstrating the power of ArcGIS system in transforming the fire department operations from preparedness to real response and recovery. In case of project objective, the main goals of this project is to demonstrate how ArcGIS tools can support fire departments in managing fire safety inspections for both building and fire hydrants, and also to identify and mapping the potential fire hazards within the community. Okay, this is a solution architecture. This architecture illustrates how ArcGIS technology is used to modernize and streamline fire department operations. The core of the system is a web GIS platform supported by ArcGIS server to ensure all information is accessible, reliable, and protected. It enables key functions like pre-incident planning, target hazard analysis, and fire service mapping. Use tools like ArcGIS Online, ArcGIS 123, and ArcGIS Fields Map. The system allows access via desktop, web, and mobile. This providing a tilde tools for executive decision makers and field operators, and also promoting the public engagement to support data sharing and fire risk awareness. Hence, we have a decision support cycle. These decision support cycles, as you can see here, it's helpful planning, security, and service, also decision support in general. Professional GIS here who operate behind the scene to manage data infrastructure and perform special data analysis that feed into the operational system. ArcGIS have different capabilities, almost 6 to 7 capabilities. So among of those ArcGIS capabilities, my solution based on one ArcGIS capabilities, which is field operations. Why? Because it enables real-time data collection, mobile access, and efficient communications between decision makers and field operators. So allowing these firefighters and emergency responders to collect, share, and act on spatial information directly from the field. So right now I'll go to demonstrate and show you how ArcGIS system is capable for field operations. As I said, we have supported ArcGIS tools, which are Survey 1, 2, 3. That is a tool that can help field operators or GIS professional to prepare a survey form, which can help him or her to collect data directly from the field and can be used or can be accessed just using your mobile. And you can work on it even if you are offline, if the location does not access an internet. So there is special fields which have been prepared just to help the field operators to collect this data which can help him or her for fire safety inspection, especially for building. So the first fields which inspector should fill it is building name. He must tell us the building name. As you can see here on the map, the building name can be seen well. So if the field operator doesn't know the name, he can just go and see on the map and fill here. Like here it is Muimbili, so I come here to write is Muimbili Hospital. After that, we must give her the location of that building by pointing just here. After that, he must tell us the building use type. As you can see here, there is a lot of selections or sections like commercial, residential. So you must choose one of building use type. And construction material, you have to know the constructed material used to construct that building, and also to know how to know how many number of floor within the building, how many number of exit door for emergence, how many number of occupant, estimated occupant within the building. Also, we have to know special fire, a critical fire equipment or fire systems. As you can see here, we have to know if the building have fire extinguisher, yes or not. And if there is one fire extinguisher, we have to know which type of fire extinguisher based on the materials or things which are contained within the building. And here it is extinguisher condition. We have to know it is outdated, poor, or needs service. Also, we have fire protection system, fire alarm, smoke detectors, speakers. So we have to know all these if have been installed, and also we have to know their conditions, if they're working or not working, if they need some service, we have to know. After that, inspector or the field operator must take the photo of building. Here we have to know the inspector name and also the inspection date. After filling all these form, he must submit this form. And all this data which have been collected use this form can be visualized using a dashboard. The dashboard provides comprehensive overview of structure condition, fire safety measure, and inspection status across various facilities. It visualizes data like building use type, number of floors, number of occupants, emergency exit, and also it has an interactive map which display inspected buildings, while charts like pie charts help us to summarize the types and condition of fire extinguisher. Also, the dashboard track the presence of critical safety equipment. Like you can see here, this fire protection system, fire alarm, smoke detectors, And as you can see here, there is some indicators that shows the total number of building that has been inspected. And here you can just see there is a list. Here is a list of building IDs, and there are some details which show the conditions of this fire protection system. And when you want to know maybe how many buildings you have been inspected for a month, maybe you want to know from 2nd June maybe until 2023 June, 23rd, as you can see here, it's only 6 buildings which have been inspected, and total number of buildings which are missing all fire protection system and 3. And you can see here speaker systems are 3, smoke detectors are 4, and fire alarms are 3. So this dashboard, it is interactive. If you want to know buildings which contain 150 occupants, if you just click here, it shows total number of buildings are 7, and within all, out of 27 buildings, 7 buildings are there is no any missing protection system, but you can see here out of 27, 4 they are missing, out of 7, 4 are missing, and out of 7, 1 out of 7, you see here only 6 they installed smoke detectors, and 7 also stored all fire system. And if you want to know just directly the condition to know, okay, how many buildings they have expired fire extinction or due just for replacement, you can just come here and shows. And if you want to know maybe, okay, I just want to know their condition directly, you may just come here. Sorry. You may just come here and click. If you click, just show the condition directory where this building is located, and a pop-up will appear here, show you all the information, also the picture that has been taken by field operator, as you can see here. So this dashboard supports informed decision-making for fire risk mitigations and prioritizing safety improvement. So after performing this fire hazard shift, there is another form which our inspector can fill it to show us to identify the potential hazard which are within the building, and can see there is hazard category, hazard detail, hazard risk level, and action required based on the operator comments and the status, if it is solved or it is in progress or not resolved. Also, we have to know to take the picture, inspector name, and date. After that, there is also a special dashboard which provide a visual and data-driven overview of fire hazard and risk across the inspected facilities. And it highlights hazards such as absence of evacuation, improper chemical storage, and the lack of critical system like fire alarms, like smoke detectors, and each requiring a corrective corrections which does action required based on operator comment. And you can see here there is a list which show those hazard detail provided by operator, actions required based on the comment of operators, and the potential fire hazard which have been mentioned directly from the feed. As you can see here, also we have an interactive fire hazard reporting map. So when you have to know how many buildings are in progress and how many buildings are just not resolved, if you just come here, it shows the number. It is total of 4 sites or 4 buildings they are not resolved, and maybe their risk is also very high. So you want to know how many cities they have high risk fire hazard. When you click it here, it shows 7 fire hazard they have high risk of, or they increase the likelihood for a fire to occur. If you want to know the status, how many building sites they are not resolved the problem, you can see here 4. So, um, high risk level, emphasizing the urgency for fire safety improvement. And this dashboard play a vital role in monitoring, assessing, and supporting decision making for fire hazard reduction and facility safety upgrade. Um, And these are general benefits for having these dashboards and special analysis. So this dashboard and special analysis tools provide insight into fire trends, incident hotspots, and response performance, and supporting informed decision making. By conclusion, modernizing fire department operations with GIS is not just about maps, it's about saving lives and improving infrastructures, building safer communities. So I recommend further expansion for this system because it has just been demonstrated in Dar es Salaam. So I recommend it to expansion of this system to other cities and integration with emergency alert system. I also plan to continue building capacity in geospatial innovations to support public safety and smart urban development. I would like to sincerely thank Israel Eastern Africa for this incredible learning experience and my mentors, especially Joven Vincent, for their support and guidance. I am grateful for this opportunity to contribute, grow, and innovate through GIS. Thank you. Um, I would like to welcome if there is anyone who have questions or any comments. So right now I would like to welcome my colleague, Mr. Dennis. He has amazing and entertaining ArcGIS solution to present today. So Mr. Dennis, you're most welcome.
Thank you, Faisal. Nice presentation. Good morning, good afternoon, and good evening to everyone joining the call. Faisal, can you stop sharing? Okay, so thank you. My project title is FTTH, which is Fiber to the Home Planning and Optimization using ArcGIS. So a brief profile about myself. I'm Dennis Kiogora, a telecommunications and information graduate engineer from the Jomo Kenyatta University of Agriculture and Technology with a background in radio access network planning, fiber network design, and project management, working on both mobile and fixed network technologies. For the last 3 months, I've had the opportunity to deepen my expertise during my internship here at Esri Eastern Africa, the Nairobi office, where I've been actively exploring how ArcGIS can be applied to solve real-world network infrastructure and planning challenges. So this project focuses on designing a high-capacity fiber optic network for Konza Technopolis, which is my focus area, using latest GIS tools to ensure efficiency, accuracy, and cost-effectiveness. The goal is to build a spatially accurate and scalable FTTH network model from the central office all the way to the customer's doorstep, by leveraging the ArcGIS utility network framework for smart connectivity and analytics. As we know, fiber to the home is critical to delivering fast, reliable internet to growing urban areas. Traditional FTTH planning methods often rely on static datasets and manual engineering processes that are time-consuming, prone to errors, and inefficient in adapting to dynamic urban and rural development. So as network rollout scale, fixed capacity planning becomes essential to avoid over-provisioning and under-provisioning of infrastructure, to reduce capital expenditure and operational expenditure, to accelerate time to market for broadband services, and lastly, to quickly resolve customer complaints and downtime of network. For my proposed solution, I decided to use ArcGIS as it offers a robust geospatial analytics, network modeling, visualization capabilities that operators can use to design networks based on real-life constraints, such as terrain, building density, infrastructure availability, and also can perform service demand focusing using demographic and development data that you can find on Esri, to your database. Model fixed capacity requirements in alignment with geographic clusters and customer density, visualize performance and capacity in real time using dashboards and spatial reports. So a quick rundown through my network. So I'll have the OLT, which is the optical line terminal that is located at the main office. And this forms part of the core network that connects the main fiber office to the regional hubs. Then I'll have the distribution splitter, which is part of the distribution network that serves access areas through the splitters and manholes. Then we'll proceed to the access network, which delivers and acts as an intermediary point between the drop hub and the manholes. So it forms part of the access network. Then lastly, you'll have the drop network, that is the drop hub and the ONT. The ONT is the network interface unit at the customer end. This entails the routers at the clients. So each of these layers were carefully mapped and attributed with the installation data and cable capacities and cost values. So for my solution architecture, I utilized ArcGIS Pro for data collection, where I started with a clean geodatabase, and I applied the communication utility network foundation asset package and customized it to match my FTTH network design, which I'd specifically used for Conza. With this, I mapped down the demand points. These are the customers and the base maps over here. Then I digitized the fiber cables across the distribution zones, then using logical naming, attribute domains, and snapping to ensure precise connectivity. For example, each fiber cable was classified by type. For example, the distribution core had 48 core fiber, then automatically attributed with the length and capacity of the fiber. Still on ArcGIS Pro, I mapped out the clusters and defined coverage of the service area, and I calculated the fiber routes and capacity design and optimization models over here. For the cost analysis bit, once the network was in place, I implemented a cost model, which I calculated using fields. I added the lengths and the total costs of the different fibers and equipment. Then using the field calculator, I multiplied each feature's geometry-based length with its costs per meter to get the dynamic totals. That really helped in the cost analysis. After completing the data collection on ArcGIS Pro, I published the layers to ArcGIS Online, where I was able to build dashboards for the stakeholders. These dashboards shows key stats such as the total fiber length of the network, the estimated project costs, and the number of clients connected to the network. These visuals make it easier for planners and investors and field teams to track the project's progress without needing technical GIS skills. So the reason I utilize the communications utility network asset package, which is offered by S3, is it supports network connectivity and associations. This enabled me to map out the different layers based on the capacity and the port port allocations. This is essential when you're planning out a large scale utility network. For my case, I'd mapped out to serve at least 10,000 clients. So it also supports dynamic tracing and analytics. This will enable us to perform upstream and downstream tracing to analyze fiber paths and detect outages and optimize maintenance and expansion for planning. As you know, one of the biggest problems facing fiber deployment is fiber cuts, which causes downtime, hence customer complaints. Also, the use of this utility network allows for scalability, as it can be deployed throughout the country as a national grid. Also, asset modeling and topology validation. Lastly, we have branch versioning, which allows different teams to work on the geodatabase without applying locks or duplicating data. This is essential when you are dealing with multiple teams using your geodatabase. For example, you can have different fiber teams supplying a different municipality. So this is where the use case comes in. So once I mapped out everything, this is how my network looked like, sorry. It starts off here at the main office. This is where I had provision. You have all the provisioning for your clients. As you can see, my main office, the capacity was to serve 10,000 clients. This is important as you can be able to know the amount of splitters that you will require to serve 10,000 clients. This is the bit where under provisioning and over provisioning of your network comes in, and such a solution is important as it comes to mitigate this. Then from the main office, I have the backbone fiber. This is purple, as you can see. The importance of these colors is, as you all know, different companies, operators have different fiber optic cables, and this comes to play when you're terminating a different fiber core for different operators. So the color coding is essential as it avoids errors where team members on the ground end up cutting down cables illegally. So as you can see, my distribution cable is purple. You have the status, we have the capacity that it carries, we have the length and the cost field over here. This will be crucial in the cost analysis. Then from there, it trickles down to the splitter. Then based on our planning, my splitter requirement is 1:64. This will support all the 10,000 clients. Again, goes to show how important the solution is, as you can plan for a whole network while seated on your desktop. It trickles down to the access cable over here, the blue one. Then we have the here access hub that streams down to the drop hub. The drop hub connects the clients to the network. So the last node here over here is the client. And from the client's point, you can see the device that they are using. You can see the customer ID, their contact details, if they've paid, the billing status, the service plan, if they want 20 Mbps, this is where you can see. Then from this, I was able to generate a dashboard which shows the cable costs of the whole network. As you can see here, we have the access cable costs, distribution cable, drop cable. This table over here is connected to a field map that is updated by the field team and also the clients, the customers on the ground. I'm going to demonstrate that. So once the client or a new customer wants a service request, it automatically updates on the dashboard, and the field team back in the office can use this information to configure the new client into the network. We also have pie charts here that show the billing status of the clients. This is important when it comes to planning, as it can also be used as a service qualification analysis tool, because a customer can request for service, and if they haven't paid yet, well, they'll be pending over here, but at least you'll know that there's a certain client who wants service over here. So let me quickly show a demonstration of the field map and how the real live data comes into play here on the dashboard. Just a minute. I hope I'm clear. So this is the field map that the field team can download on the phone, even the clients. So I'll open up my map over here. As you can see, let it load. Sorry. My GPS is on. That's why it has taken us to Upper Hill. Yeah, sorry. So as you can see, here's the network. So say a field team member wants to install a new client, say, let's put him over here. Also, another bit, all these configurations are done using the communication utility network. For example, a certain drop hub cannot serve, say, more than 3 clients over here. That's essential to know. And it can be used by the planning team to provision for more or less clients. So if I want to add a new client, okay, say over there, gonna give him an ID, say from number over there. The lat long will automatically pick. The fiber ports will be allocated back in the office. The billing status too. Service plan say they want 50 Mbps. You can put all this information over here, then update. So it's submitted. As you can see there, that's on my phone. So I want to stop sharing. So if we come back to my map over here, I hope I'm visible. Yes. As you can see, this is the new client has automatically been updated into my geodatabase. And from this, the planning engineers back in the office can allocate the different capacities that this client want. And also they can check the service qualification analysis. Perhaps they've utilized all the fiber resources that they have and they can't serve this client. So this is important for the guys to know the return of ROI of this service and whether the client can be added into the network. So as I come to the conclusion, this project has real life applications. where it can support ISPs, which are internet service providers, and utility planners in planning scalable fiber networks. It can support field technicians during installation and inspection of fiber networks. And lastly, municipal authorities in approving and budgeting telecommunication infrastructure. Yeah, so this marks the conclusion of my presentation. I'd be happy to answer any questions, but for now, I'll share the platform to my colleague, Jolie.
Hello, everyone. My name is Jolie Sinao Baraza, and I have a diverse academic background in food science and technology from the University of Nairobi, complemented by training in software development through ALX. I have also developed a strong interest in GIS, and as a Q2 SRE intern, I've gained valuable hands-on experience working on real-world GIS projects. I've had the opportunity to learn directly from professionals in the field, which has helped me improve my technical skills, understand how to apply GIS in practical situations, and approach problem solving more effectively. So my project is about visualizing underground infrastructure in Nairobi using ArcGIS. This project addresses the challenge of managing and planning sewer infrastructure in rapidly urbanizing areas. Many towns in Kenya struggle with incomplete, undocumented, or outdated sewer networks, leading to maintenance difficulties and inefficient service delivery. By applying ArcGIS technologies, this aims to help map, analyze, and visualize sewer systems to support data-driven decision making. My study area is Waitethia, and it is located in Juja Sub-County, Kiambu County, Kenya. It is characterized by unplanned and semi-planned developments with high population growth and increasing demand for sanitation infrastructure. There's also limited existing sewer coverage. I chose Waitethia because of the need to improve the wastewater management, and there's also a high risk of groundwater contamination and environmental degradation. And it is also ideal for demonstrating GIS-based sewer network planning and monitoring. So Waitethia, like many towns, has no updated sewer records or inspection routines, which increases vulnerability to system failure and environmental contamination. It also lacks a centralized digital sewer map, making it difficult to coordinate maintenance, detect blockages, and support urban planning. And as a result, there's frequent overflows, delayed repairs, and rising health risks. So to solve this, my project proposes a GIS-based system to map, inspect, and manage the sewer infrastructure in Waitethia. Sorry. So first, engineers will map all manholes and pipes using ArcGIS Pro, and this will create a complete digital layout of the underground infrastructure. Next, we'll centralize the data on ArcGIS Online, allowing utility managers to access and update sewer records anytime. Sorry. Urban planners will also be able to interact with the data through a web app built with Experience Builder, which helps visualize the underground infrastructure and guide expansion. Field inspectors will also use mobile tools like field maps to assess manhole conditions on site and record photos, status, and any urgent issues, and their updates will feed directly into the system in real time. Ultimately, this setup supports faster maintenance planning and a more transparent sanitation system, which will benefit engineers, planners, and the entire community. This diagram represents the solution architecture for my GIS-based sewer infrastructure project. The process begins on the left with field survey data collectors who use tools like field maps to collect real-time geospatial and attribute data from the field. This data is then stored in a cloud-based geodatabase, which allows it to sync across the ArcGIS ecosystem in real time. And then ArcGIS Pro is where all the data undergoes processing and geospatial analysis. Once it is processed, the data is published to the web portal that is ArcGIS Online, where it will become accessible across various applications, sorry. And from there, the information is made usable and shareable through tools like ArcGIS Experience Builder, which I will use to create interactive web apps for visualizing the infrastructure, and dashboards to provide a high-level summary and real-time monitoring of assets, and then field maps, which will allow ongoing data collection and inspection directly from the cloud. And finally, the right side of the diagram highlights the stakeholder management. The system supports multiple levels of access, that is professional GIS analysts who will manage and analyze the data, urban planners and engineers who will use these insights to guide development, and executives who will require summaries and oversight dashboards, and public access depending on the sharing permissions. So this architecture ensures that all stakeholders have access to up-to-date and accurate spatial information. The ArcGIS capabilities that enabled me to complete this project are mapping and visualization using ArcGIS Pro, data collection and field mapping using ArcGIS Field Maps, hosting layers and web maps using ArcGIS Online, displaying terrain and elevation differences using ArcGIS Experience Builder, and real-time infrastructure monitoring and stakeholder engagement using ArcGIS dashboards. So this is the sewer infrastructure map for Waitethie, showing all pipelines and manholes with detailed clickable pop-ups for each feature. The map includes two main layers, that is pipelines shown as colored lines and manholes shown as points. When I click on a manhole, a pop-up appears showing its ID, manhole name, the year it was built, the coordinates, the height, the elevation, the diameter, the pipe size, the structural description, whether it was made from concrete or composite, and defects and repairs if there's any, and the repair history and the cover type. And I've also added photos of each manhole so that users are able to visually assess the assets without actually visiting the field. This makes the map a quick reference tool for engineers, planners, and field teams. So this here is my Experience Builder web app, which is designed to help us visualize the elevation changes along sewer pipes and manholes in Waitethia. It is useful for understanding the slope, flow direction, and terrain challenges that affect how our, our sewer system performs. On the left, we have a dynamic list of all the sewer pipes, each one labeled by its ID. And when a user clicks on a pipe, it zooms into that pipe segment. And at the same time, the elevation tool here at the bottom displays a cross-sectional view showing us how the elevation changes along the length of the pipe. And this makes it easy to see whether the pipe runs downhill as intended or if there are any problematic dips. So as you can see, we've clicked pipe 1. We can see that the elevation is at 1493 meters, and as we move, the elevation rises to 1495, So here we can see there's a steady slope. Yeah, there's a steady slope, and this tool is valuable for multiple stakeholders like planners can use it to assess if existing routes are suitable for expansion. Engineers can use it to verify whether pipes follow the right slope or for proper sewage flow. And inspectors can see where there are low points and where the manholes are likely to collect dirt. So this app saves time because before this, we will have to analyze each pipe's profile manually using ArcGIS Pro or on paper. But now anyone can access the pipe's elevation profile right on their browser. I have created this dashboard to give a real-time interactive overview of the sewer infrastructure in Witedia, particularly the condition of pipes and manholes, the materials used in this, and the inspection schedules. So on the left, you can see there's a summary um, indicators showing that there's 49 manholes and 45 pipes that have been mapped. And the dashboard breaks down important attributes like the pipe material. As you can see, there's HDPE, PVC, or steel. There's also the manhole cover type as composite or steel, and the repair history of manholes as average, bad condition, good condition, or sealed. So when I click on good condition, we're able to see how many manholes are in good condition, and that is 19 manholes. And we can see that 7 manholes are in poor condition. We can also check the cover type. For composites covers, there's 19 manholes and 9 manholes are made of steel. So for the repair history, it helps us understand the physical condition of the manholes and the pipes too. And for the pipes, we can see that 6 pipes are made of HDPE material and 12 are made of PVC material. And this makes it easy for the planners and engineers to inspect and verify assets visually. There's also a inspection table, and this table shows upcoming inspections for each manhole, and it helps our field team plan their visits efficiently and ensures that no asset is missed. So this table is connected to the field map, whereby when an inspector is in the field, they can they have a form to fill, and when they fill the next inspection due part, it reflects on the dashboard and they're able to access it easily. And they're able to track progress and how many inspections are pending or how many are due. There's also a chart here that gives us a clear view of how many inspected manholes require repair versus how many are in acceptable condition. It gives our maintenance team a priority list and helps assess how critical the current network health is. So if you're seeing 40% of the inspected manholes need repair, that's a strong case for allocating urgent maintenance resources or requesting more funding. So this dashboard is designed not just to display data, but to reveal patterns and help us answer questions like, are some materials failing more than others? Or where are the poorest conditions concentrated? And are inspections being done on time? And what's the real workload for repairs this month or this year? So I will share my phone screen to illustrate the field map. So this is the mobile inspection tool I've built using ArcGIS field maps, and it allows our sewer maintenance team to access manhole locations, record inspections in the field, and synchronize that information in real time with our central database. So when we open the app, we see a live map of all the sewer manholes in Witedia. Each point represents a mapped manhole captured with GPS and linked to its attribute data. So you may ask, how do field inspections work? So when an inspector taps a manhole, say that one, from there they can view the past inspection history or begin a new one. They can also view the attributes of this manhole. So for the field inspections, here, as you can see, there is no past field inspection for this manhole, so you can add a new one. So this form, there's a form they fill. They can take a photo of the manhole to show the condition of that manhole at that time. They can fill in the inspector name, inspection ID, the inspection date, the manhole ID, the cover condition, if there's any debris present, if there's any repair needed, any comments they have, and the next inspection, when the next inspection is due. All of this information is stored in as a related record. So it stays linked to this specific manhole, but it doesn't clutter the map um, with extra layers. And once the information is submitted, it is synced back to our GIS system and becomes available to planners and utility managers through our dashboard or map viewer. This means that we no longer have to rely on paper reports or delayed data as the information is readily available. This field map also has offline capabilities in that even in areas without internet, inspectors can be able to continue working, and the map and forms are downloaded to the device, and once they reconnect, the data is synced automatically. So this app is designed for field inspectors in the sewer maintenance team, but the data they collect directly informs the work of urban planners, engineers, and public health officers. And by using field maps in Witede, we are able to transform how sewer infrastructure is managed. We are also able to improve public health outcomes and reduce maintenance delays and build a digital system that can scale as the town grows. Also, when the inspectors are in the field, they can be able to add a point when they spot another manhole. So say they can be able to add manholes or pipes. And and once I save, it will update to the map in real time and also the dashboard and the web app. Thank you. I've come to the end of my presentation. If there's any questions, please feel free to ask. And I'd like to thank Esri for giving me this opportunity to learn and grow in the in the GIS field. Thank you. I'd like to invite Wesley Kirui to continue. Let me just stop.
Okay, good morning, good afternoon, good evening, everyone. Welcome to this presentation. I'll be demonstrating how we can use ArcGIS to effectively manage waste. So my name is Wesley Kirui. I have a background in geography from Bwani University. and I'm an aspiring solutions engineer, passionate in leveraging spatial analysis and problem-solving skills to drive innovative solutions. I have had an insightful experience here at S3 Eastern Africa, and I've had a chance to learn and explore the ArcGIS capabilities from the best solution engineers. So as by my project topic, I have identified various problems experienced by the authorities that are responsible for managing waste. The first problem I identified was on data management, whereby there are problems of record keeping. Also, we have a problem of visualization, and then a system of engagement whereby the public and the stakeholders are not able to engage and share ideas. They also have a lack of proper monitoring and inspection tools. Now, this is where the ArcGIS becomes a handy tool in solving this problem, whereby we will be utilizing the ArcGIS Pro to integrate data on waste bins, installed waste bins, and integrate them with collection routes within the city. And then after we share it online, whereby we will be able to create field maps, survey 123s, and ArcGIS dashboards. So my project objective was to develop an ArcGIS solution for management and monitoring of waste. Some of the other objectives that will support my main objective include mapping all the waste bins, mapping all the collection routes, and developing a real-time management and monitoring dashboard. So on my solutions architecture, I classified it into 3 stages. And the first stage is data collection, whereby we will be utilizing field maps and surveys 1, 2, 3 to collect data on the locations of waste bins. We'll also use it to capture images of the waste bins. Using also the existing map layers, we'll be able to get data on municipal boundaries. And then we'll get the routes data by digitizing the imagery, OpenStreetMaps, and also shapefiles from the KENHA, that's an authority managing the highways in Kenya. All these, we will integrate them using ArcGIS Desktop, and then publish it to we host it online so that the solutions engineers and the GIS specialists will be able to create field maps and surveys 1 to 3 for the end users, whereby they'll be accessing it in form of desktop, web, and also in form of mobile devices. So from the desktop, we'll have the GIS analyst will be making analysis, and then we will have the stakeholders and the executive accessing it in form of dashboards and story maps. We'll also have our end users here as the public accessing it in form of survey 1 to 3, and also the other end user will have the collection crews and the inspectors accessing it in form of field maps. Now, after collecting all the information we need, after collecting all the data about the collection pins and the routes, now using ArcGIS Pro, we'll be able to integrate everything and come up with an interactive map as one displayed here. So in this map, it captures the accessible routes and also captures the locations of each pin. Now each pin here carries some information whereby we can know the material it's used to construct. We can know the condition, and we can know the waste type for collecting the waste type dumped in that bin. So when we click in one of the pins, we are able to see the category. It's a dumping pin. We can also see the waste type. This one is for general. You can also see the capacity, the material, and also the route used to access that pin. Same case with another pin here. If we click, see this one is an organic waste type. Then the capacity is 150. It's made of metal. So this interactive map enables us to see or get information about a certain pin without being in the field. Moving on, after now assembling all this data in ArcGIS Pro, we will share it online, whereby we'll use it to develop dashboards. This one is for executive and stakeholders, whereby they'll be using to monitor the conditions of pins, and also to monitor how the activities are done in the field. So with this interactive dashboard, the executive in the office can be able to tell how many dumping points are there within the city. For example, this one shows a total of 123. And within the same dashboard, it has been classified whereby they can be able to filter and see the categories, whereby we have dumping. Is it a dumping bin or is it an open landfill? So if they select a dumping bin, they can see the exact location, and also they can tell the number of all the dumping bins. And then also if they select an open landfills here represent the uninstalled bins, whereby the waste are littered. So they can tell the number and also the location. Sorry. Also within the same dashboard, the executive can be able to monitor which bins are in good condition, which bins are in poor condition, which one require maintenance, and which one are under maintenance, or how many. So if they select those ones with good condition, they can be able to see the number and also the locations of each. They can also be able to filter those in poor condition. They can tell the number. The same case to those which require maintenance and those ones which are under maintenance. Suppose also the executive want to know the collection routes, how many collection routes are mapped. So within the same dashboard, they can filter to see the routes and the dumping pins are located along that route. For example, I used the initials here to label Nairobi City Route 1. So when they select that route, they can be able to see only those pins which are located along that route, and they can tell the number of pins along that route. So as you can see, there is one here which is not along the route. So it means that this pin has not been assigned any route, and the city managers can be able to view and assign a route to that pin. Same case with these other routes. You can be able to filter and see all those pins along that route. Also within the same dashboard, there's an analysis chart whereby it creates a percentage to compare landfills with dumping pins, so that in case there is an increase in the other slice, maybe the open landfill slice is increasing, they can be able to make informed decisions earlier and act accordingly. So with this chart or pie chart, they can be able to view all dumping pins, the representation in the map when they select, and also they can be able to view the open landfills when they select. Moving on to another dashboard. Sorry. Yes. This one also is for executive and stakeholders who can be those authorities managing the environment. You can be the NEMA in case in Kenya. This dashboard can be used to manage or to monitor inspections in the field. It can also be used to allocate collections. So suppose a stakeholder in the office wants to know the total number of dumping points. It's indicated here. There are a total of 126 within the dashboard. And suppose he wants to filter to know how many dumping pins, how many dumping sites. Dumping sites here are the endpoints whereby the waste are dumped after collection. So in case he wants to know the number and the locations of each, he will just click that and filter. You can see the dumping sites. We have 3 here. So this one at the corner, and then 2 down here. The same case with open landfills. Also, the dashboard can provide us with analysis bar charts, whereby we can be able to see the materials used to construct the pins. The dashboard can tell you how many pins are constructed using metal, how many are constructed using plastic, and how many are constructed using concrete. For example, when the stakeholder or the executive want to know the location of those pins which are only constructed with metal, they can be able to filter, see the number, the 67, and when they look at the map, they can be able to tell the location of each pin. Same case with those ones constructed with concrete. We have 3. That's the dumping sites mostly constructed with concrete. We have also those constructed with plastic. These are mostly located along the public areas. Also, this dashboard enables us to monitor the condition of each dustbin, whereby we can know how many, using a serial chart here, we can be able to know how many bins are in good condition and how many are in poor, how many are require maintenance, and how many are under maintenance. So this chart categorizes bins according to the waste type. We have organic waste bins, we have the general waste bins, and we have the recyclable waste bins. So in case a stakeholder want to know the total number of those general waste bins, how many are in good condition, by just selecting that bar, they can be able to see the locations of each, they can be able to see the number. The same case with those organic bins, which are in good condition. The same case with the recyclable, which are in good condition, they are 9. So when you go to poor condition, they can be able to see which ones are in poor condition. For example, here we have, I think 2. Those ones which are in poor condition, we can see they are distributed all over. The same case with those ones which require maintenance. So with this, they can be able to make decisions earlier and say and send a field inspector or crew to attend. We also have a chart here which summarizes the pin condition. This one is for analysis purposes. So they can say out of the total, 11% of the pins are under maintenance, 56% are in good condition. We have those ones which are in poor condition, which represent 23%. Then we have 9%. So the beauty of ArcGIS dashboard is that it provides you with an analysis. An executive also can be able to filter to see which pin is assigned to which inspection route. So an category selector here enables us to select maybe to see only those pins which are assigned to a certain route. So for example, this one labeled NCC is initials for Nairobi City County Route 1 as inspection route. So it's labeled here with using purple color. So the executive can be able to see that how many pins or which pins are assigned to these inspection routes. The same case to route 2, they can be able to see those pins which are assigned to that route. And then the same case with route 3. Within the same dashboard also, there's a table which is used for inspection when an inspector in the field used as a field map to inspect. His or her records is captured in the dashboard, and then it is shown that how the inspector ID and then the total number of inspections he or she has done in the field. So it's captured here within the same dashboard. This dashboard can also be used for collection, whereby a pin is assigned to a certain route. So vehicles are assigned to a specific route labeled here, categorized in 3 colors: purple, blue, and green. So it's easier to monitor the collection schedule, and also to monitor the changes in case to monitor in case there's a complaint that the waste are not being collected. So it's easier to make a follow-up. Up to that far, that this comes to an end of my presentation. So I'll take this opportunity to make a sincere appreciation to ESRI Eastern Africa, the ESRI team, for giving us this or for giving me this platform to learn and also they explore the capabilities of ArcGIS. So I'll welcome if there's any question. Let me hand over the mic to my colleague, Daniel, to make his presentation. Thank you.
Thank you, Wesley. A wonderful presentation. Good morning, good afternoon, everyone, and thank you for this opportunity to share my work with you today. My name is Daniel, and over the course of this internship, I've focused on applying geospatial analysis to support urban flood resilience in Mathare, one of Nairobi's most densely populated and flood vulnerable communities. This presentation walks through the simulation workflow I developed using ArcGIS Pro, the insights I generated, and how those findings can support planning, disaster risk reduction, and community action. So, why Mathare? Mathare is home to over 150,000 plus residents, many living in informal settlements along steep slopes and riversides. With rapid urbanization, impervious surfaces have increased, while drainage systems have remained limited, putting lives and infrastructure at risk during seasonal storms. My goal was to translate rainfall data into spatial insights so that planners, responders, and communities could make informed decisions before, during, and after flood events. My simulation aims to achieve my project objectives was to develop a flood simulation model for Mathare using real rainfall inputs, identify high-risk buildings, roads, and zones under varying rainfall intensities, support planning decisions with visual and data-driven evidence, and prototype a scalable workflow for future hazard modeling in urban Kenya. I used a range of data sets and geospatial tools: rainfall from CHRS satellite precipitation data, terrain SRTM 30 meters digital elevation model, land cover from Sentinel-2 classification for surface flow sensitivity, building footprints from Google Open Buildings version 3, software from ArcGIS Pro with special analyst for hydrologic modeling, and communication tools, dashboards, and story maps for outreach. I also tested the integration with Google Earth Engine to enrich the analysis with building height estimates. To simulate flooding in Mathare, I used ArcGIS Pro to build a step-by-step hydrologic model. Starting with rainfall input from CHRS, I processed elevation data to generate flow direction and accumulation layers. From there, I delineated basins and runoff models to produce the flood depth, velocity, and water surface elevation outputs. Finally, I overlaid these results with building footprints and land use to assess the exposure, and this workflow was applied to both medium and high rainfall scenarios for comparison. Here we have an interactive map for Mathare, showcasing the building footprints as the gray sections. Now, to translate analysis into impacts, I designed a solution architecture where at the center is a centralized geodatabase where key spatial layers, the rainfall, the digital elevation model, buildings, and basins are all managed. And I used ArcGIS Pro for simulation and hydrological modeling, then pushed the outputs to the web environment for broader accessibility. On the front end, I developed a story map for public engagement and awareness, and a dashboard for disaster response teams to monitor real-time exposure. The architecture supports multiple levels of use, that is from the executive access for planners and policymakers, public access for interactive visuals, and technical access for professional GIS users for future model refinements. This flexible framework makes the system scalable to other informal settlements in Nairobi. While the maps are still processing, I'll briefly highlight the core outputs that the simulation generates. The flood depth layers to identify where water levels exceed safe thresholds, a flow velocity maps to assess erosion risk and emergency accessibility, and surface water height elevation layers that help compare flood levels against ground and building heights. These special insights are valuable to urban planners designing flood resilient infrastructure, disaster response team prioritizing high-risk zones, community organizations advocating for housing upgrades and drainage improvements, researchers and policymakers developing long-term climate adaptation strategies. Even without the visual layers at this stage, the outputs allow us to quantify flood exposure, showing how many structures are impacted and where risks escalate under different rainfall intensities. The results form the basis of targeted interventions, planning decisions, and community advocacy. Now, by overlaying the simulation layers with building footprints and estimated building heights, I could begin to ask which structures are at risk, how many homes fall below floodwater levels. This exposes the vulnerability of critical infrastructure in homes, especially those with low elevation and minimal vertical clearances. The ability to quantify exposure opens doors for targeted interventions. Among the key findings was that over 2,000 plus buildings were exposed under extreme rainfall. Footways and secondary roads are mostly affected, and critical access roads are submerged by levels greater than 1.5 meters. Now, the raw rasters alone can't reach the people who need this information the most, so I developed a dashboard a prototype ArcGIS dashboard showing real-time exposure summaries. Now, to make the simulation results accessible and actionable, at the top, on the side, sorry, you see the number of buildings affected to close to 4,000 structures identified as either partially or fully flooded across both rainfall scenarios. Red displays the partially flooded under extreme rainfall. Blue for partially flooded under moderate rainfall. Yellow for the ones, okay, this is a light green for fully submerged under extreme rainfall. And the pink represents, the purple represents for fully submerged under moderate rainfall. The side panels will allow users to explore different rainfall intensities and view trends over time using the charts. And the summary charts shows that some buildings are exposed to extreme rainfall more than others. And on the right, another graph breaks down flood exposure by rainfall scenario, helping planners to visualize how risk escalates when the intensity doubles. Here for fully submerged and partially flooded. The dashboard is designed not just for GIS professionals, but also for urban planners, local officials, and community-based organizations who need to quickly identify at-risk zones and prioritize response efforts. The value of this simulation goes beyond the model itself. It's designed to be actionable across multiple sectors, like urban planning, using the flood depth data to guide infrastructure upgrades, drainage improvements, and safer building codes in informal settlements. Disaster risk management, identifying priority zones for early warning systems, evacuation routes, and emergency preparedness. Community engagement, sharing accessible visualizations through dashboards and story maps to inform residents and support grassroots preparedness. And policy development, giving decision makers credible, especially grounded evidence to support long-term climate resilience strategies. Because everything is geospatial and modular, this framework can scale, whether it's for another ward in Nairobi or other rapidly urbanizing flood-prone areas. But like any model, it has assumptions like the constant soil saturation and runoff coefficients, the no storm drain infrastructure or underground flow was accounted for, and short storm durations were used for scenario comparison. The next step could include incorporating longer rainfall time series, calibrating with historical flood extents or community reported data, modeling the effects of green infrastructure interventions as well. The project has grown both my technical GIS capacity and appreciation for human stakes for spatial planning, from raster processing to reducing vulnerability. It's all interconnected. I've deepened my skills in ArcGIS Pro, Earth Engine, dashboard design, and storytelling, all by being part of a mission that matters. To wrap up, flood simulation is more than a technical exercise done right. It saves lives. With good data, smart tools, and collaborative partnerships, even small teams can generate big impacts. Thank you to the team at S3 Eastern Africa for the mentorship, the tools, and support, and I look forward to your insights. Thank you. I will pass the mic over to Eunice.
Um, Good morning, good evening, good afternoon, from wherever you're watching from. My name is Eunice Wairima, and my project is on ArcGIS platform for strategic mineral marketing and promotion. The term strategic mineral means critical minerals for high tech, defense, or industrial sectors and green energy transition, among which most of them are used in battery metals and electronics. Again, my name is Eunice Harima Aweru, a geospatial engineering graduate from the University of Nairobi. I'm passionate about uncovering patterns, making sense of complex spaces, and using maps to bring clarity to the world around us. Enjoy blending technical skills with creativity, and I'm especially drawn to how GIS can support smarter decisions in areas like infrastructure, environment, and everyday life. A brief introduction of my project. Um, the mining sector is increasingly merging as a commercial frontier with the potential to drive economic transformation. But in Kenya, a network of public, private, and advocacy institutions shapes its mining profile both locally and internationally. So while we have geological survey maps which show significant mineral potential, the true value only lies in how well these opportunities are marketed, financed, and translated into productive ventures. The problem statement of this project is despite the diversity of actors and potential mineral assets, Kenya mining sector still relies heavily on traditional promotional methods like expos, brochures, and fragmented websites. And this limits interactivity and spatial intelligence. Hence, falling short in today's data driven investment landscape. My case study is the Bell in Moyale, um, which shows the maroon area, highlights the maroon area that is an ultramafic rock. And an ultramafic rock forms in high temperatures and pressures, usually below the crust, and sometimes are lifted to the surface during tectonic forces. Um, if you look keenly inside the rock, the ultramafic rock, you can see a symbol named US. That means a serpentinite, and close to it you can see talc. These are called lithological structures in geology. So for serpentinite, it's an altered ultramafic rock, the maroon area. A serpentinite is an altered ultramafic rock, which when exposed to heat and water becomes a serpentinite, while talc is a carbonated serpentinite. So in these lithological structures, we shall examine the presence of gold and chromite in this study. My objectives for the project is to develop an interactive story map where investors can access spatial data that they wouldn't access in just an analog map for decision making. Um, the project also suggests visibility of location data and resource estimation data, which the investors will use to inform on their next steps after the desktop analysis. The ArcGIS capabilities used here are ArcGIS Pro, which I used for my image preprocessing, for false color composite, band ratio analysis, and advanced symbology for mapping mineral potential zones. The ArcGIS Online provided a cloud platform to publish and share spatial data, enabling easy access, collaboration, and stakeholder engagement. The ArcGIS Story Map brings about interactivity, clarity to the result by combining maps, narrative text, and multimedia for strategic mineral promotion. So this is my solution architecture. And at the input is where I first downloaded satellite Landsat 8 um, data from USGS, which I later pre-processed to clean the bands, because initially when you download, they are not clear. So once you pre-process, they become clearer and you get a clear composite image to work on. So down here, once the um, information has been downloaded and um, cleaned, it's where right after the desktop analysis, geologists and mining engineers can use this data for their geochemical and geophysical um, uh, analysis once they're satisfied with the desktop analysis. So the data goes to the ArcGIS portal to manage geographic information to efficiently share and collaborate. And at the ArcGIS Online to manage geographic content in a secure and cloud-based environment. The output can be accessed on desktop, web, and devices, and the outputs are story maps and dashboards, which can be used by researchers, students, investors, mining companies, name it all. So my methodology began by downloading the Landsat 8 imagery, which I performed an atmospheric correction using a statistics calculator tool from ArcGIS Pro to give a corrected image. Then an area of interest was extracted from combining the 7 bands to give a composite. Contrast enhancements were performed, and they include the band ratio, uh, which is a form of dividing two digital numbers to enhance visibility of one aspect compared to another, which is not needed in the study. Band ratio combinations are borrowed from researchers, which discriminate lithological units. In this case, in which gold and chromite falls in, and hydrothermal alteration indicates the evidence of existing serpentinites, like I showed you from the geological map that hosts chromite, gold, and other associated minerals. The raster A, B, C, and D that follows after this page will clearly indicate the relation between the lithology and the hydrothermal alteration, as well as the geological map. So as you can see, figure A is shows lithology based on existence of chromite. You can see it's yellow to medium purple tones. Lithology based on gold. You can see it still highlights the same lithology, where here it's purple to pink, and at figure A, it's yellow to pinkish tones. And the hydrothermal alteration ends, you can still see the communication is constant. It highlights the rock in which serpentinization took place, which is a form of hydrothermal alteration, where these 4 images indicate the presence of gold and chromite in that area. The results of this project proves effective in lithological and hydrothermal alteration mapping, which are critical for identifying potential mineral deposits. So by integrating these insights into an ArcGIS map, this research bridges Kenya's mineral potential with an interactive digital platform, transforming static data into an engaging tool for investor attraction and strategic outreach. I'll go straight to show you my story map. So the untapped mineral potential dominated by a serpentinite known to host gold and chromite and other base metals is the region highlighted in maroon, which further details are seen through the image processing. Slide 2 aims to show the previous workings by small scale miners in the region, indicating presence of gold, chromite, and other minerals. So this is a product of lithological calculations based on gold, which highlights the purple pink area. And based on hydrothermal alteration, still highlights the same basement in which gold is expected to occur. Chromite band ratio combinations produced this raster imagery, which still communicates with the two above. And lastly, the hydrothermal alteration based on gold still highlights the same basement in which chrome and gold are expected to occur, and that's in blue color. So for the reserve estimations of the minerals in question was calculated on ArcGIS Pro with an estimated depth of 10 meters and specific gravity for each. Specific gravity is density for each mineral. And calculations gave 594 trillion US, whereas for chromite, that gave 1 billion US plus. So this concludes to the Bell standing out as a prime target for structured exploration and responsible investment. I'll go straight to demonstrate the output of my data. So that is the Bell area. As you can see, that's the ultramafic rock. From the key, you can see that color stands for ultra basic is the same as ultramafic, and it hosts serpentinite, which is a product of hydrothermal alteration of the ultramafic rocks. So that being my area of interest, images downloaded from Landsat 8 were pre-processed to give clean bands, clean and clear bands. Let me just show one. As you can see, this is clear with no haze. They were done individually from bands one to band 1 to 7, but what was used in the study is band 2 to 7 because that's where minerals give their spectral signatures. After that, band ratios were calculated. Like I said, band rationing is dividing one digital number by another to bring out um, a visible something more clear than what you don't need. And for this study, we were examining gold and chromite. So based on research, the band ratios were combined to show lithology for gold and chromite, as well as that of hydrothermal alteration for chromite and gold. This is attributable where um, tonnages of gold were calculated and that of chromite to eventually give resource estimations for each. That marks the end of my presentation. I would like to thank Esri for giving me this opportunity to learn and grow and interact with the amazing people in the company. Thank you. I'd like to welcome any questions.